I would like to warmly welcome everyone. Let me briefly introduce the key details of this Excellence Diploma project. The work was prepared by Kinga Kocsis, graduating architecture student. The thesis supervisor is Domokos, and the co-supervisors are Hartvig and Répás.
I would like to warmly welcome the Honorable Committee and everyone present. My name is Kinga Kocsis, and I would like to present my dual-focus Excellence Diploma project, titled The Soft Cube. I would like to begin the presentation with my motivation, why I decided to undertake a diploma with two distinct focuses. After that, I will introduce the geometric focus, followed by the architectural focus. If I had to describe my own motivation, I would place it within the triangle of geometry, art, and understanding, and I would explain it through the interaction of these three ideas, which continuously shape and influence one another in a subtle but meaningful way. For each pair, I brought a specific example. I would begin with geometry and understanding. Plato formulated the regular solids and identified the elements of the world with these perfect geometric bodies. Through geometry, he attempted to reach understanding, examining how the world is segmented and how it is constructed in a clear and ordered way that reflects deeper principles. It is important to highlight here that the only Platonic solid capable of filling space without gaps or overlaps is the cube. Geometry and art. For the relationship between geometry and art, I brought an installation by Attila Ciorgu, one of our committee members. This work shows how a strict geometric idea can unfold into an artistic experience that feels both analytical and playful. In the installation, three regular solids transform into a fourth one, and with a small adjustment, the transformation can even produce the fifth regular solid. For the relationship between art and understanding, I brought three small images. In the first one, we see a work by Sol Lewitt, who created conceptual pieces and explored ideas through very precise, systematic artistic methods. In his work titled Variation of Incomplete Open Cube, he approached an extremely complex combinatorial problem through an artistic lens, examining how many different ways a cube can be made incomplete by removing edges, and how these variations can still preserve the essence of the original form. In other words, he sought understanding through art. The starting point of my geometric focus is essentially the idea of space filling. And now I would like to connect this concept to architecture as an art form, because the way we occupy and articulate space is one of the fundamental architectural gestures. We can see space filling in its basic form, for example in building a seamless brick wall, where every element fits together without gaps. But we can also approach it more abstractly, as a rule system that determines how we cut something out of a large empty space. In fact, we could even define architecture through this deliberate act of shaping and organizing space. In my geometric focus, I work with soft cells and soft fillings. These are forms without sharp corners, yet they are capable of filling space without any gaps or overlaps. The topic already has a bit of history. In one of the papers, the authors proved that there exists an algorithm that can take convex polyhedral fillings and turn them into soft fillings, while preserving both the combinatorial structure of the original filling and the positions of its lattice points. However, the paper does not address the question of how one could find all soft versions that correspond to a given polyhedral lattice. In another paper, the authors use the filling based on the truncated octahedral cell, shown here on the slide, to demonstrate that if the symmetry group is defined in advance, then it becomes possible to determine exactly how many soft fillings can be created for a given polyhedral lattice. In this particular case, when the full symmetry of the truncated octahedral filling is preserved, these two soft cells can be obtained. Here I marked one of the nodes of the filling, where 4 edges and 4 cells meet. I highlight this because both the paper and my own thesis rely on a so-called edge-bending algorithm, which focuses specifically on nodes. In other words, we build the entire pattern outward, starting from these nodes. The idea here is that if we zoom in on a single node, we can draw unit-length half-tangent vectors along the edges that meet at that point. Then the algorithm starts to move these vectors independently, and through this motion they sweep out a sphere. After a while, they settle into a pattern that makes the overall configuration smooth. The key condition for this to work is that at every corner there must be a pair of tangents pointing in opposite directions. In the language of equations, this means that their product is equal to -1. From equations of this form, we build systems of equations, and by solving these systems, we achieve the softening of the pattern. In this way, a smooth node becomes visible. In my thesis, I focus on softening the cubic lattice. In a single node of this lattice, 6 edges and 8 cells meet, which already gives a sense of the complexity of the problem. The soft cubic cell shown here in the image was the only known soft cube cell when I began my research, so it can be considered the genesis of the entire investigation. The main question of my thesis was how many soft cube cells can be generated if we do not impose any prior symmetry constraints. To explore this, we modified one step of the edge-bending algorithm, and instead of solving the equation systems on a sphere, we solved them on a discrete set. In this setup, the half-tangent vectors may point only in the 6 directions defined by the cubic lattice. We also required that the edges of the soft filling must be planar curves, meaning spatial curves are not allowed. Under these two conditions, the soft filling partially agrees with the cubic lattice in second order and remains parallel to it. In the first theorem, we proved that these node softening equation systems admit exactly 12 possible solutions. In the second theorem, we show that out of these 12, only 4 equivalent solutions ensure that all 8 meeting cells have softened corners. And this particular node is precisely the node of the genesis cell. All the remaining solutions turn out to be unsuitable, because as we can clearly see here, sharp corners inevitably appear in those cases. In the third theorem, we prove that all soft cube cells produced in this way have a prismatic structure. This means that there is always a projection direction, such that every cross-section perpendicular to it becomes a square grid, allowing these cells to be stacked into tower-like formations. This phenomenon also appears in nature, and here I am showing basalt columns which form characteristic hexagonal prisms. Based on the first 3 theorems, we can conclude that this single node type is the correct one. From here, we need to zoom out. Instead of examining one node in isolation, we must also consider how nodes are oriented relative to each other, so we begin rotating them accordingly. With this approach, we identify 4 types of curved edges, determined by the orientation of the half-tangents. These orientations can either coincide or oppose each other, and for a complete analysis, we also include their mirror images. Here it is important to emphasize that we are not prescribing the actual geometry of an edge, only the orientation of its half-tangents. For example, instead of drawing a semicircle, we could use any other curve, as long as it arrives with the same half-tangent configuration. From these edge types, we then generate face types. We take a face, apply the softness condition, that every corner must contain a pair of opposite tangents, and place the curved edge types around it. We perform this construction in every possible way, and this gives us the 6 types of curved faces. It is important to note that types 2 and 3, as well as types 4 and 5, are mirror images of each other, and at this stage, these pairs still have to be treated separately. After this point, the problem reduces to placing 2 opposite curved faces relative to one another, since we already know the pattern will be prismatic. But it is not enough to pair the 6 faces with the other 6. We must also examine their relative orientation, which introduces the factor of 4. We rotate the configuration around the z-axis by 90 degrees, giving 4 distinct positions. And with face type 4, we see that even a single face can produce 4 different geometries. This gives us 144 configurations to examine. And from here, we must determine when 2 cells are identical. We performed a manual analysis, and I also wrote a computer program to verify the results, which I will now present. The program takes the edges as input, together with the orientation of their half-tangents, encoded as 0s and 1s depending on whether they point upward or downward. From this, it automatically generates edge sequences while preserving the softness conditions. Using the 4-element edge sequences, it produces the curved face types. We see more letter combinations than 6 because the program already accounts for the relative orientation of 2 faces, so it generates every curved face in every orientation. For this reason, the program performs 256 face pairings instead of the previous 144. We specify the transformations under which 2 cells can be mapped into one another, and then we combine these transformations so that every cell is generated in all possible orientations. In the final step, an identity function applies every transformation combination to every cell and compares every cell with every other one. Through both the manual analysis and the computational verification, we obtain the main theorem of the thesis. There exist exactly 26 distinct soft fillings that are second-order partially compatible with the cubic lattice and parallel to it. Here we can see, in just a moment, all 26 distinct cells. The curved faces are marked with Roman numerals, and the overlines indicate the rotations around the z-axis in steps of 90 degrees. On the left, you can see them generated using the curved face types, and on the right, the same structures appear in the physical model shown at full scale. And as an interesting observation, if we examine the surface elements of the cube, we find that it has 8 vertices, 12 edges, and 6 faces. And when we add these numbers together, we arrive once again at the total of 26. We are not claiming that there is a direct connection between these two facts. At this stage, we simply do not know. But it is, in any case, a very striking and rather thought-provoking coincidence. It is also important for me to mention, in connection with the soft cells, the concept of fundamental domains. These are minimal sets of elements that make it possible to shift the pattern, and they are essential for demonstrating that a given cell truly fills space. And in the 5th theorem, we show that 68 different fundamental domains can be constructed for the 26 cells, and we organize these into 8 distinct classes, which together describe the full range of ways these structures can generate a complete filling of space. So when we look at the fundamental domain for this particular cell, we do not necessarily see immediately how many reflections or rotations are required to produce a shiftable unit. In this case, the domain consists of 8 elements, and it corresponds exactly to this white region here. And I can place this unit next to itself in any direction, and with that we can demonstrate the space-filling property of the cell. And here you can see all 68 fundamental domains displayed alongside the 26 soft cells. With this, we have essentially created a closed universe. And as an additional point of interest, I would like to show what happens if we do not modify the edge-bending algorithm. That is, if we once again solve the equation systems on the sphere, and we also allow spatial curves to appear. In that case, we obtain extremely unusual and intriguing geometries, shapes for which we do not immediately see that they are cubes, nor that they are space-filling. But if we look at them long enough, the cube gradually becomes visible within the structure. And with this idea, I would like to guide the attention toward the architectural focus. To capture architecture in a geometric way, I set myself yet another geometric challenge. My intention was to arrange these 26 elements in some meaningful and coherent manner, especially since they form a kind of closed universe. So I decided to place them inside a 3x3x3 cube, arranging them throughout the volume, with one position intentionally left empty, because of course we only have 26 cells. Here, we can see that in the case of simple cubes, this is a straightforward task. In fact, if we take 26 elements and place them in such a grid, there are more than 10 to the power of 20 different possible arrangements. However, in our situation, every single element is distinct. So the question was whether there exists a configuration in which every curved face and every planar face fits perfectly to its neighbor, so that the entire object is completely face-to-face, without any mismatches. Well, we weren't entirely sure that such a configuration existed, but after writing down many rules and constraints, I completed the construction, and it does exist. And now I would like to show this assembly. And it is also important for me to mention that at the very heart of the entire object right in its center, we find the original Genesis soft cube cell. So in a very natural and almost elegant way, the initial cell returns. It reappears at the core of the structure. From this point onward, this object became the central focus of my architectural exploration. I then searched for a site that could meaningfully resonate with it. And that site became Muley Point in Utah. The remarkable feature of this location is that an extraordinary network of natural fractures has formed there, both deep inside the rock mass and across its surface. We see these enormous, almost regular cubic blocks, and I want to emphasize once again that this is entirely natural. We are not looking at a quarry. And these cube-like formations appear at multiple scales, ranging from blocks with 3-meter edge lengths all the way up to ones measuring 18 meters. And here you can see that this is quite an extensive phenomenon. It is not only present locally. In the middle image, you can see the exact wall segment I chose as the design site. And in the first image, the view from the top of that wall looking out over the San Juan River Valley. This place is unique because until around the 13th century, Pueblo peoples lived here, and one of their architectural traditions was to use the cliff face as shelter and build directly into it. And this was the tradition I wanted to connect to with my architectural proposal, allowing the project to resonate with the long-standing relationship between architecture and the rock itself. The idea was to place my design soft structure into this natural, very strict combinatorial system in such a way that it always follows the fracture network. In this way, a truly unified relationship between the combinatorial structure and the soft structure can appear. This means that I always think in the scale of the given row of the fracture pattern. Here you can see my actual site plan, and here is the specific wall segment itself. And looking closer, we can already observe that the main fracture runs across the cliff face at an angle of about 45 degrees. To be able to work with this fracture network, I needed to abstract it in some way, aiming to stay as faithful as possible to the real geometry, while still bringing the scale of the rows to clean, rounded values. And through this process, cube sizes of 3, 6, 9, and 18 meters in edge length emerged. And here you can see the assembled object at the end of the composition. The idea behind the placement concept was that the logic of this assembled object, its structure and the way it comes together, should appear throughout the entire mountain. So the individual elements, all 26 of them, are scattered across the site, allowing us to experience each one separately, in its own position and at its own scale. And at the end of the path, we finally encounter the fully assembled object, giving us the chance to understand the whole system in a clear and complete moment. To organize the sequence, I turned again to mathematics and created a Hamilton path, a graph in which every vertex is visited exactly once, and the route unfolds without repetition. So the entire journey follows this Hamilton path, ending at the large assembled cube, 9 by 9 by 9 meters, while each individual element measures 3 by 3 by 3. In this way, the walk becomes a gradual revelation of the object's internal logic, step by step, until the full cube finally presents itself as both a mathematical structure and an architectural experience. Here you can see the circulation system. For the vertical movement, I imagined carved stone stairways, drawing from Pueblo traditions, and once again following the fracture network. The horizontal movement would happen on cantilevered platforms, which would be made from artificial materials. Here you can also see the 26 elements, and I wanted to present them as carved caves, again inspired by Pueblo practices. This means that we always perceive the relationship between two curved surfaces, so the geometry of each cell appears as a negative space. And in this way, moving through the site, we can experience each element individually, in the order in which the full object is assembled. Each cave entrance is marked by a solid continuous surface, clearly indicating where the carved space begins. And the caves themselves always follow the scale of the corresponding row, keeping the geometry consistent with the underlying system. Here you can see the blocks affected by the carving, and next to them the elevation view. This means that the entire vertical circulation takes place inside the wall, following the fracture network, while the horizontal circulation reinforces the natural pattern of the cracks as it unfolds across the cliff. This is roughly how I imagine the whole system. For the material choice, I was thinking of copper, because the goal was to match the natural environment as closely as possible in color and tone, and let the difference appear only in the surface quality, in the texture, and in the way the material catches the light, revealing the presence of something intentionally added. The structure of each station looks roughly like this. Everywhere, there is a carved stone cave, a carved stone stairway, and the path itself. And here you can see how the entrance of the cave is marked by a solid surface. The path is made from perforated copper, and its stiffening elements, the railing supports and the structural braces, take on the form of two-dimensional soft cells. I tried to carry this logic through all the details, so that even the smallest components reflect the same underlying idea. This is more or less how I imagine one of these stations. With this approach, I hope to offer a new perspective on the river valley itself, and on this remarkable natural fracture network, allowing it to become walkable and experienceable from close range. The concept for the assembled object again follows the idea of a Hamilton path, but here I drew a Hamilton cycle into the structure. This means that I pass through each element exactly once, and then return to the starting point in a clear, continuous loop. It is interesting because if I had 27 elements, a Hamilton cycle would not be possible in this graph. But with 26 it is, the approach to the object would happen from the missing element, which becomes the natural entry point. Here you can see the floor plans, using the same notation as in the mathematical part. And at this stage it becomes clear that the vertical circulation also takes on this planar soft cell form. I imagined it as a suspended staircase, gently following the same geometric logic throughout the entire system. The openings receive the same form as well, meaning that an opening appears only on the wall, where movement is possible along the Hamilton cycle, making the direction of travel very clear. With this, I essentially designed a directed labyrinth, one that guides the visitor step by step. For the interior space, my concept was that we should perceive the boundaries of the elements, to sense that this is a space-filling structure, while still being able to see through the entire system. Transparency was important, which is why I chose perforated copper as the main material. The perforation pattern itself is a two-dimensional soft cell. I associated the levels of perforation with the surface qualities of the landscape. A denser version as an analogy for solid rock, a more open one for crushed stone, and the most transparent version for the fine, distant curves that appear across the terrain. And this is how the object itself would be layered. As I mentioned, the genesis cell sits at the very center of the cube, and I marked it with a solid surface. This makes it clear that the mass becomes denser as we move from the outside toward the inside, offering the widest possible views toward the valley and the cliff, while still letting us feel the internal stratification. Here, you can see how each opening appears exactly where the Hamilton cycle allows movement. Even in the details, I tried to use the soft cell motif, shaping the joints according to this form, and applying the same logic to the stiffening and the spacing of the slabs. This is how I would like the cliff face itself to become walkable. And this is how I wanted to integrate my designed soft cells into this very strict and very rigid combinatorial structure, letting the two systems meet gently. Thank you very much for your attention and for following the entire process.
Classical symmetry, dynamic symmetry, and even origami folding all demonstrate that mathematics is not a dry or rigid discipline, but a source of pure beauty.
What we see here suggests that there may not be many places or many architecture schools where such integrated, dual-focused work can emerge. It is a rare environment that lets a project stand firmly on two legs, combining mathematical structure with architectural experimentation.
I started thinking in this direction because the whole subject inspires me deeply, and it occurred to me that if scholars of the 6th to 8th centuries had had the opportunity to consult with Kinga Kocsis, Islamic architecture might have explored an even more intriguing path, especially in the development of stalactite-like spatial formations that could have enriched its expressive vocabulary.
The known world suddenly turned toward us with an unfamiliar face. And that made me realize that this cell system also offers a completely new way of seeing space.